In the stillness before dawn, when the world sleeps and stars pierce the darkness with their ancient light, there exists a place where humanity has constructed its most ambitious instrument of understanding. Deep beneath the Swiss-French border, some 100 meters underground, the European Organization for Nuclear Research, known to the world as CERN, operates a machine that defies ordinary comprehension. The Large Hadron Collider, a circular tunnel 17 kilometers in circumference, accelerates subatomic particles to 99.999999% the speed of light, crashing them together in a controlled violence that seeks to recreate the first microseconds of the universe itself. And in doing so, it has begun to reveal something that may fundamentally alter our understanding of reality's deepest nature, a crack, as it were, in the edifice of everything we thought we knew. What does it mean, one might ask on such a contemplative night, when the instruments of science whispered to us of asymmetries where we expected symmetry, of unexpected particles where we found only empty space, of fundamental forces behaving in ways that defy our most elegant equations? It means, perhaps, that we stand at a threshold. Not the threshold of knowledge, for that threshold has always existed, and humanity has spent its entire conscious existence standing at that peculiar juncture between the known and the utterly unknown. Rather, we stand at a threshold of humility, a moment when our theoretical frameworks, constructed with such mathematical precision and philosophical care, have revealed their incompleteness. Part 1. The Ancient Desire to Understand. To understand the discoveries at CERN, one must first contemplate the deeper human impulse that drives such endeavors. We are pattern recognition creatures, evolved over millions of years to perceive subtle regularities in our environment. A rustling in the grass might indicate a predator. A change in cloud formations might suggest approaching weather. The positions of stars in the sky offered our ancestors both calendar and navigation. This fundamental capability, to perceive order within apparent chaos, to discern the underlying rules that govern phenomena, has never ceased its operation within us. We took this capacity, refined it through millennia of careful observation, and eventually formalized it into what we now call science. But science is not merely the cataloging of observations. At its deepest level, it is the quest for unity, the belief, which has proven remarkably justified, that the same fundamental principles operate throughout the cosmos. When Isaac Newton discovered that the gravitational force pulling an apple downward was the same force holding the moon in its orbit and the planets in their paths around the sun, he revealed something profound. The universe is not a collection of disconnected phenomena, but an integrated whole governed by discoverable laws. This unification, this reduction of apparent complexity to underlying simplicity, became the supreme goal of physics. 3 centuries of scientific progress have been marked by successive unifications. Electricity and magnetism, initially understood as separate forces, revealed themselves to be different manifestations of a single electromagnetic force. Light itself emerged as an electromagnetic phenomenon, a ripple in the very fabric of space and time. The weak and strong nuclear forces, initially mysterious, became integrated into frameworks of stunning mathematical beauty. And throughout the 20th century, physicists pursued what many consider the ultimate dream, a unified field theory that would show all forces as different facets of a single, elegant principle. This dream remains unrealized, yet never before has it seemed more tantalizing. With each discovery, with each extension of our knowledge toward higher energies and smaller scales, we approach something fundamental about reality. The question that animates CERN, that draws thousands of physicists from nations across the globe, is not merely practical or technical. It is existential. What are the deepest laws of nature? What is the universe made of? What principles hold it all together? And what do these principles tell us about our place within the cosmos? Part 2. The Cathedral of Understanding. Before one can appreciate what CERN has begun to question, one must first understand what has been built, a theoretical structure of such power and elegance that it stands as one of humanity's greatest intellectual achievements. The standard model of particle physics is not a single discovery, but rather a vast architecture constructed over nearly a century by countless physicists, each contribution laying another brick in a building of breathtaking sophistication. At the foundation lies a simple but profound principle. The universe, in all its apparent complexity, is made of elementary particles. Not just atoms, as we learned in childhood chemistry, but entities far smaller and more fundamental. The electrons that orbit atomic nuclei, the quarks that compose the nucleus itself, the photons of light, the W and Z bosons that mediate the weak force, all of these, the standard model tells us, are elementary particles. They are fundamental, irreducible, the basic building blocks from which all matter and energy are constructed. These particles interact through four fundamental forces. The strongest is the strong nuclear force, which binds quarks together into protons and neutrons, and binds these nucleons into atomic nuclei with such power that immense energies are required to separate them. The electromagnetic force holds electrons to nuclei and atoms to atoms, giving rise to all chemistry and biology. The weak force, responsible for certain types of radioactive decay, operates at subatomic scales and is crucial for the processes that power the sun. And gravity, the weakest force by far, but the most familiar to our everyday experience, shapes the large-scale structure of the cosmos. What renders this conceptual edifice so remarkable is not merely the unification of these forces into a coherent mathematical framework, but the precision with which the standard model's predictions have been verified by experiment. When theoretical physicists, working only with mathematics and principles of symmetry, predicted the existence of particles before they were observed, and then experimenters found those particles exactly where and with the properties predicted, it vindicated not only specific theories, but the entire scientific enterprise itself. The standard model's accuracy is extraordinary. Its predictions confirmed to many decimal places, its framework producing results that align with observation in nearly every conceivable test. Consider for a moment what this means. Humanity, a species that emerged barely 1 million years ago, living on a tiny planet orbiting an ordinary star, has used the unique gift of consciousness and mathematics to decode the fundamental nature of reality itself. We have determined the rules by which the universe operates. We have built a framework so comprehensive and so accurate that it can predict the results of experiments not yet performed. By any measure, this is an astonishing achievement, a triumph of human intellect that would seem impossible to explain except through the recognition that the universe operates according to principles that the human mind, itself shaped by cosmic evolution, can in some measure grasp. Part 3. The Whispers of Incompleteness. Yet even in the moment of its greatest triumph, the standard model harbored within itself the seeds of its own insufficiency. As physicists tested its predictions to ever greater precision, as they explored the universe across ever more extreme energies and conditions, certain anomalies began to emerge. Quiet at first, like the distant rumble of distant thunder, these discrepancies suggested that something fundamental remained unaccounted for. The first and perhaps most obvious problem was gravity itself. Newton's theory of gravitation, refined by Einstein's general relativity, describes gravity as a bending of spacetime itself caused by mass and energy. This is a beautiful and elegant theory, confirmed by countless observations. Yet it is fundamentally incompatible with quantum mechanics, the framework that governs particle physics. At the scales that CERN explores, at the energies where particles interact, the effects of gravity are utterly negligible, too small to measure. But at even higher energies, at the Planck scale where quantum effects of gravity might become significant, the two frameworks diverge fundamentally. A complete description of nature must unify gravity with quantum mechanics, yet for nearly a century, this has remained an unsolved problem. But this was not the only crack. There was the matter of antimatter, or rather, the terrible asymmetry in their abundance. The Standard Model predicts that when the universe was born, in the first microseconds after the Big Bang, equal amounts of matter and antimatter would have been created. Yet when matter and antimatter meet, they annihilate one another in a burst of energy. If equal amounts had been created, everything would have annihilated, leaving only radiation and no matter at all. Yet here we are, a universe made of matter, our atoms of matter, our very bodies of matter. Somehow, inexplicably, there was slightly more matter than antimatter in the early universe. For every billion antimatter particles, there was 1,000,000,001 matter particles. And it is from that infinitesimal asymmetry that all the stars, galaxies, planets, and living beings in the universe emerged. The Standard Model cannot explain this asymmetry. It remains one of the deepest mysteries in physics. There was also the puzzle of dark matter and dark energy. Astronomers observing the motions of galaxies discovered that the visible matter, stars, gas, planets, all the luminous stuff we can see, accounts for only about 5% of the total mass and energy content of the universe. Some 27% is dark matter, a form of matter that does not interact with light but exerts gravitational effects. And approximately 68% is dark energy, even more mysterious, a form of energy that seems to permeate all of space and is causing the expansion of the universe to accelerate. The Standard Model is essentially silent on the nature of these invisible constituents that comprise 95% of the universe. It is as if we have built an elaborate theory to explain a small corner of reality, while the vast majority of reality's substance remains utterly mysterious. And then, there was the problem of the Higgs boson itself, or more precisely, the problem of mass. In the Standard Model, particles acquire mass through their interaction with a pervasive quantum field, the Higgs field. But the calculations suggest that quantum corrections should make particles vastly more massive than they are observed to be. Why are electrons so light? Why are quarks so light? The Standard Model, without introducing new physics, cannot answer these questions. It is as if the universe has been carefully tuned, with parameters adjusted to particular values that allow for the existence of atoms, stars, and ultimately life. Such fine-tuning struck many physicists as deeply suspicious, suggesting that something fundamental was missing from the theory. These were not fatal flaws in the Standard Model. It continued to make predictions that were confirmed with remarkable precision. But they were like small cracks in the foundation of a great cathedral, visible to those who examined closely, suggesting that beneath the beautiful surface lay something that needed deeper understanding. The physicists working at CERN, therefore, were not merely testing a theory they believed was complete. They were searching for the deeper theory that would encompass the Standard Model while answering the questions it could not address. They were seeking the more fundamental layer of reality. Part 4. The Apparatus of Discovery. To discover the crack that unravels everything, one must first look where the cracks are most likely to appear, at the highest energies, where particles interact with such violence that the structure of spacetime itself might be strained. This is why the Large Hadron Collider represents such a profound investment in the human quest to understand the fundamental nature of reality. It is the most powerful particle accelerator ever built, designed specifically to reach energies where new physics might reveal itself. The operation of such a machine is a marvel of engineering and physics combined. Protons, the nuclei of hydrogen atoms, are accelerated to nearly the speed of light and injected into the circular tunnel. They circulate around the 17-kilometer loop thousands of times per second, guided by powerful superconducting magnets cooled to nearly absolute zero. Electromagnetic cavities aligned around the ring add energy to the protons with each pass, accelerating them to higher and higher velocities. The process continues until the protons reach energies of several trillion electron volts, energies that did not exist naturally anywhere in the universe since the Big Bang itself. At designated collision points around the ring, beams of protons traveling in opposite directions are brought together. The intersection is not precise. The protons are not like billiard balls that can be made to collide at a single point. Rather, the beam profiles at the collision point are carefully controlled, and when they cross, occasionally protons will indeed collide head-on. In these collisions, the kinetic energy of the protons is converted into mass, creating new particles. And among these newly created particles might be the evidence of physics beyond the standard model. What makes this search so challenging, however, is that these new particles, if they exist, are not created in every collision. They are rare events, appearing perhaps once in billions of collisions. The machine must therefore operate at incredibly high luminosity, producing billions of collisions per second. The data recorded from each collision is enormous, measured in terabytes per second. Sophisticated computer algorithms, the products of artificial intelligence and decades of development, must sift through this torrent of data to identify the rare signals that might indicate something new. The physicists working with this apparatus understand themselves to be engaged in an enterprise fundamentally different from merely testing predictions. They are hunters of the unknown, searching for signals in noise, seeking the traces of forces or particles that have never been observed. In this quest, they employ not only the tools of experimental physics, but also the methodology of science itself. The careful formulation of hypotheses, the design of experiments to test those hypotheses, and the willingness to be surprised by nature. It is work that requires immense patience, for it may take years of running the machine, analyzing data, and refining techniques before any signal becomes clear enough to declare as a discovery. Part 5. The signal in the noise. Science often proceeds not through dramatic eureka moments, but through the slow accumulation of evidence, the gradual shift in probability as data accumulates. So it has been with CERN's latest findings. Working across multiple detector experiments, massive structures weighing thousands of tons, buried beneath the Earth, capable of recording the traces of particles created in the collision's aftermath. Physicists have observed anomalies that collectively suggest something is amiss with our understanding of fundamental physics. The anomalies are subtle. When certain particles decay, they do so in patterns that deviate slightly but consistently from the predictions of the standard model. When other particles are created in the collisions, their properties sometimes differ from what theory predicts. These are not massive deviations, not experiments showing results off by an order of magnitude. Rather, they are deviations of a few percent, precisely measured deviations that appear when you examine billions of events and extract their statistical properties. Any individual measurement might be explained away as a fluctuation, a statistical artifact. But when multiple independent measurements all deviate in the same direction, when the deviations appear consistently across different experiments, the probability that they are merely statistical noise becomes vanishingly small. In classical physics, an anomaly is something that breaks the rules. In quantum mechanics, anomalies have a deeper meaning. They represent fundamental asymmetries in the laws of nature that cannot be cancelled by any choice of renormalization. The anomalies that CERN is detecting appear to violate something called lepton universality. This is a principle enshrined in the Standard Model that states electrons, muons, and tau particles, the three charged leptons, interact identically with a weak force that mediates radioactive decay. They differ in mass, but their fundamental interactions should be identical. Yet in certain decay processes, this universality appears to be broken. The weak force seems to couple with slightly different strength to electrons versus muons. What makes this particularly intriguing is that similar anomalies have been detected in different channels, different types of particle decays, all pointing toward a violation of lepton universality. The significance of these measurements has grown over time, as more data has accumulated and more sophisticated analyses have been performed. Each new measurement pulls the conclusion further away from what the Standard Model predicts. Physicists calculate the probability that such deviations could occur purely by chance, through statistical fluctuation. The probability shrinks with each new data point. What once seemed like a possible statistical fluctuation begins to take on the appearance of a genuine signal. But this is only one anomaly. There are others. Measurements of the muon's magnetic moment, a quantum property that describes how the muon interacts with magnetic fields, show a small but persistent deviation from theoretical predictions. The electron's own magnetic moment shows analogous tensions. The mass of the W boson, measured with incredible precision, differs slightly from what precision electroweak fits predict. These individual anomalies might each be explainable as experimental or theoretical artifacts, but together they begin to paint a picture of a universe that does not quite conform to the Standard Model we have so carefully constructed. Together, these measurements hint at new physics, new particles, new forces, new principles operating at the fundamental level. The question that animates the CERN community is not whether anomalies exist, but what they mean. Do they represent genuine deviations from the Standard Model, or will continued data-taking and refinement of theoretical calculations eventually reconcile the observations with existing theory? History suggests that sometimes new physics is revealed in such ways, but other times apparent anomalies resolve themselves. The only way to know for certain is to continue the quest for understanding, to push higher in energy, to measure with greater precision, and to follow where the data leads. Part 6. Theories of the Beyond. If CERN's anomalies represent genuine signals of new physics, what might be the nature of this new physics? The theoretical physics community has proposed numerous possibilities, each suggesting different ways that reality might extend beyond the Standard Model. To understand these possibilities is to glimpse the frontiers of our current understanding, the hypothetical territories that might lie just beyond our current knowledge. One possibility is the existence of new particles, interactions between the known particles and yet undiscovered particles that leave subtle signatures in the observations. The pattern of anomalies and rare decays might be caused by a new heavy particle that couples specifically to the weak force in a way that deviates from the Standard Model's predictions. Such particles could be bosons, force carriers like the photon or W boson, or fermions, like the quarks and leptons we already know. If such particles exist, the question becomes, why were they not discovered long ago? The answer is that they might be extremely heavy, with masses that exceed the energies CERN can currently create. But their effects could still be felt indirectly, in the subtle deviations from Standard Model predictions that appear in precision measurements. Another possibility is supersymmetry, a principle that proposes a deep symmetry between bosons and fermions. In supersymmetric theories, every known particle would have a heavier superpartner. The electron would have the selectron, the quark would have the squark, and so forth. This framework was developed to address certain theoretical problems with the Standard Model, and has the elegant feature of naturally including gravity within the quantum framework. If supersymmetry is real, it would explain the fine-tuning problems that have puzzled physicists for decades. However, despite extensive searches, no evidence for supersymmetric particles has been found. They may simply be too heavy for current accelerators to create. A third possibility is that the universe possesses additional dimensions of space beyond the three we are familiar with. String theory, the most ambitious attempt to unify all forces including gravity, naturally incorporates extra dimensions. These dimensions might be extremely small, curled up at scales far smaller than we can currently probe. Or they might be larger, with particles able to move through them in ways that would create new effects in particle collisions. If the anomalies CERN is observing are caused by particles traveling into or interactions involving extra dimensions, it would be a discovery of revolutionary proportions. There are also more exotic possibilities. Leptoquarks, particles that would carry characteristics of both quarks and leptons, could cause the patterns of anomalies observed in rare decays. Compositeness, the idea that electrons and quarks are not truly elementary, but are made of still smaller constituents, might manifest as deviations from the Standard Model's predictions at high energies. Z-prime bosons, hypothetical cousins of the Z boson that mediates the weak force, might exist and couple to particles in non-standard ways. What is remarkable is that each of these theoretical frameworks makes specific predictions that differ from the Standard Model in particular ways. The anomalies CERN is observing, if they are genuine, will provide clues to which of these theories, if any, is correct. The pattern of anomalies, their magnitudes, and their relationships to one another will serve as a fingerprint identifying the new physics at work. In this sense, nature is revealing itself not through a sudden, dramatic discovery of a new particle, but through a gradual clarification of what is amiss with our current framework. It is a subtler revelation, but no less profound. Part 7. Echoes through the universe. To contemplate the implications of CERN's discoveries is to begin to understand how intimately connected the smallest scales of reality are with the largest. Particle physics is not an isolated corner of human knowledge, interesting only to specialists in laboratories. Rather, the fundamental particles and forces we study at CERN are intimately related to the structure and evolution of the entire cosmos. Consider first the question of matter-antimatter asymmetry. Any explanation of why the universe contains matter rather than equal parts matter and antimatter must involve physics that violates the symmetry between matter and antimatter. The Standard Model possesses such violations, but they are far too small to account for the observed asymmetry. New physics, such as that hinted at by CERN's anomalies, might involve more substantial matter-antimatter violations. Such physics could have profound implications for our understanding of the Big Bang. In the early universe, mere fractions of a second after the beginning, the energies were so high that today's new physics might have been common. The asymmetries produced by this physics might have left an imprint on the universe that echoes down through billions of years to the present day. Understanding the particles and forces at CERN could shed light on why the universe exists in the form we observe it. Similarly, the dark matter problem, the fact that 27% of the universe's mass and energy is in a form invisible to light, might find its answer in new particles discovered or constrained by CERN. Some of the leading candidates for dark matter particles, such as weakly interacting massive particles, WIMPs, or axions, can be probed through the precision measurements made at the Large Hadron Collider. If CERN's anomalies indeed signal new particles or forces, these might be connected to the dark matter in ways we do not yet understand. A unified explanation of the anomalies and dark matter would represent a profound advance in understanding the cosmos. The discovery of new physics beyond the standard model would also have implications for our understanding of the Big Bang and the universe's earliest moments. The inflationary period that occurred in the first fraction of a second after the Big Bang is thought to have stretched quantum fluctuations to cosmic scales, creating the variations in density that eventually grew into galaxies. The physics of inflation depends sensitively on the properties of the particles and fields present in the early universe. New particles or interactions discovered at CERN could change our understanding of inflation, altering our predictions for what the cosmic microwave background radiation, the afterglow of the Big Bang, should look like. In turn, observations of this radiation could provide constraints on the theories being tested at CERN, creating a feedback loop between particle physics and cosmology. Perhaps most profoundly, the discovery that the standard model is incomplete would have philosophical implications for our understanding of the human place in the cosmos. For more than half a century, the standard model has been our best description of fundamental reality. Scientists have built careers understanding its implications. Engineers have designed the experiments to test it. Students have learned it as received truth. The discovery that it is incomplete, that our understanding of the fundamental laws of nature is less complete than we thought, would be both humbling and liberating. Humbling because it would show once again that human knowledge, however vast, remains finite and provisional. Liberating because it would open new possibilities, new domains of understanding that await exploration. It would remind us that the universe remains, in important respects, a mystery, and that the pursuit of understanding that mystery is a distinctly human endeavor that may continue indefinitely. Part 8. The Boundaries of the Known. Yet as CERN pushes the boundaries of our knowledge, it is important to recognize the fundamental limits that constrain the quest to understand the ultimate nature of reality. These limits are not merely practical or technical, though the technical challenges of building and operating high-energy particle accelerators are formidable. Rather, they are limits that appear to be intrinsic to nature itself, boundaries that may be insurmountable. Consider the Planck scale, a length scale approximately 10 to the minus 35 meters, a billion times smaller than a proton. At this scale, quantum gravity becomes important. The gravitational force between two particles becomes comparable to the other fundamental forces. To probe this scale would require an accelerator as large as the solar system, and would require the energy equivalent to billions of stars. Such an accelerator is not merely impractical in today's economic and technological context. It is fundamentally impossible given the matter and energy resources available in the universe. We cannot, in principle, directly observe the physics at the Planck scale. The universe itself sets a limit on human knowledge at this scale. This realization, that there exist boundaries to what can be known, limits imposed by the universe itself rather than by human limitations, has profound implications. It suggests that unified theories of everything, frameworks that would completely explain all phenomena from the quantum to the cosmic scale, may forever remain inaccessible to direct experimental verification. We may be able to construct such theories, to write down mathematical equations that supposedly describe everything, but we may never be able to prove them correct through experiment. Instead, we may be forced to rely on indirect evidence, on the consistency of theoretical frameworks, and on their power to explain the phenomena we can observe. There is also a more subtle limit on knowledge that has been recognized in recent decades, the limit imposed by quantum mechanics itself. Information about the world cannot be copied perfectly. The mere act of measuring a quantum system changes it. There exists an irreducible randomness in nature, Not everything that happens can be predicted with certainty, even in principle. The universe is not a cosmic clockwork where perfect knowledge of initial conditions would allow perfect prediction of all future states. Rather, probability and indeterminacy are woven into the fabric of reality at the deepest level. This does not render physics merely probabilistic in practice, with underlying determinism remaining unknown. Rather, indeterminacy appears to be fundamental. These limits, the Planck scale barrier preventing access to quantum gravity phenomena, the inherent limits imposed by quantum mechanics on what can be observed and predicted, form the boundaries of the territory that human knowledge can hope to explore. CERN and other experiments push relentlessly toward these boundaries, seeking to understand as much as possible before the limits are reached. This effort is not futile, even though it is ultimately bounded. Rather, it represents the highest expression of human curiosity, the drive to understand the cosmos, knowing that complete understanding may forever remain beyond reach, yet pressing forward nonetheless. Part 9. The Cosmic Perspective. To work at CERN, or to follow closely the discoveries emerging from this laboratory, is to participate in something larger than oneself, a collective human endeavor that extends backward through generations and forward into the future. It is to stand in a tradition that stretches back to the ancient astronomers who first mapped the stars, to Copernicus and Galileo who revolutionized our understanding of the cosmos, to Newton who revealed the universal laws of motion and gravitation, and to Einstein who showed that space and time themselves are dynamic, subject to bending and warping by matter and energy. In the 20th century, this tradition gave birth to quantum mechanics and particle physics, frameworks that reveal the probabilistic nature of reality and the existence of fundamental particles. The physicists who developed these frameworks, Planck, Heisenberg, Schrödinger, Dirac, and countless others, worked with the best tools and knowledge available in their time. They built upon the achievements of their predecessors while pushing beyond the boundaries of previous understanding. Now, in the 21st century, we continue this tradition. We use the tools they created, the language of quantum mechanics, the insights of symmetry and conservation laws, to probe deeper still. The physicists working at CERN are custodians of this grand tradition, but they are also innovators and explorers. They are not content to accept the standard model as a final word on reality, even though it has been so successful. They build ever more powerful machines, devise ever more sophisticated experiments, and analyze data with ever more advanced techniques in pursuit of the next breakthrough. They do this not for personal glory, though recognition certainly motivates many scientists. Rather, they do it because the quest to understand the universe is a fundamental human drive, arising from the same impulse that led our ancestors to wonder at the stars and seek to comprehend them. And it is important to recognize that this quest is not the work of isolated individuals toiling in laboratories. CERN employs nearly 2,500 people in permanent and semi-permanent positions, but the laboratory serves a community of nearly 13,000 scientists and engineers from 110 countries. The large detector experiments each involve hundreds of physicists and engineers, organized into numerous working groups, collaborating on the analysis of data. The theoretical physics community, scattered across universities and research institutes worldwide, develops the frameworks that guide experimental work and interpret the results. International collaboration on this scale is itself a remarkable human achievement, demonstrating that the quest to understand fundamental reality can unite people across national and cultural boundaries. This collaboration is not new. Since the beginning of modern science, researchers have built upon each other's work, shared findings, and worked collectively toward shared goals. The scientific method itself is a collaborative endeavor across time, each generation standing on the shoulders of its predecessors, seeing further because they have been lifted higher. CERN's existence, and the discoveries it is producing, are only possible because of this cooperative framework. The anomalies detected at CERN are significant not only because they might signal new physics, but because they represent the fruit of a vast collaborative effort spanning decades and continents. Part 10. The mystery deepens. In our modern age, saturated with information and characterized by rapid technological change, it is easy to lose sight of something fundamental about science and the pursuit of knowledge. Science is not primarily a method for eliminating mysteries. Rather, it is a structured approach to investigating mysteries while maintaining rigorous standards of evidence and logical reasoning. In the process of solving old mysteries, science tends to reveal new ones. Each answer to a question about how the universe works typically leads to deeper questions about why the universe works that way. The anomalies CERN is detecting exemplify this perfectly. Their existence is somewhat mysterious in itself. Why these particular deviations? Why in these particular measurements? Why clustered around lepton universality? The answers to these questions might involve new particles, new forces, or new principles. But each answer, once obtained, would undoubtedly lead to further questions. If new particles are discovered, why do these particles have the masses they have? Why do they interact with the fundamental forces in the way they do? Why does nature possess this particular spectrum of particles and forces rather than some other spectrum? In this sense, the crack that CERN is discovering in the edifice of the Standard Model is not a disaster or a catastrophe. Rather, it is an opportunity. It is a signal that nature still has secrets to reveal, that the universe remains fundamentally mysterious in important ways. And it is precisely this quality of mystery that drives the scientific enterprise forward. Without mystery, there would be no reason to do science, no motivation to build great laboratories and conduct careful experiments. It is the existence of the unknown that gives meaning to the quest for knowledge. The physicist and author Carl Sagan once wrote that we are made of star stuff, that the atoms that comprise our bodies were forged in the interiors of stars that have long since exploded. This profound truth connects us physically to the cosmos. But there is another connection, equally important. We are made of the same fundamental particles and governed by the same fundamental laws as everything else in the universe. When we investigate particle physics, when we conduct experiments at CERN, we are ultimately investigating ourselves. We are looking into the mirror that nature holds up, trying to understand the fundamental principles that made us possible. And in this investigation, we encounter not final answers, but deeper questions, not complete knowledge, but a more nuanced understanding of our ignorance. We learn what we do not know. We discover the contours of the mystery that surrounds us. And in doing so, we fulfill a fundamental human need, the need to understand, to seek meaning, to ask why. This is perhaps the deepest significance of CERN's discovery. It is not that a crack has been found in the Standard Model, though that is important. Rather, it is that we have once again glimpsed the profound mystery at the heart of reality, and found ourselves compelled to press further, to ask deeper questions, to seek a more complete understanding. Part 11. Peering further into the abyss. Looking forward, the question becomes, what are the next steps in the investigation of the anomalies CERN has discovered? How will physicists determine whether these anomalies represent genuine signals of new physics, or whether further data and improved theoretical understanding will eventually reconcile them with the Standard Model? The answer lies in multiple complementary approaches, each providing independent checks on the other. First, CERN itself will continue operating the Large Hadron Collider at higher and higher luminosity. The machine has been operated at only about a quarter of its design luminosity in recent years. As upgrades to the accelerator and detectors are completed, the rate of data collection will increase. More collisions mean more opportunities to observe rare processes, more statistical power to discern signals from background noise. With more data, any genuine signal should become progressively clearer, while statistical fluctuations should average out. This increase in data rate is expected to continue for several more decades, potentially providing hundreds of times more collisions than have been collected so far. Second, theorists will continue refining the standard model calculations and exploring possible extensions beyond it. The deviations CERN has observed, while suggestive, are not yet statistically definitive at the level physicists typically require for a discovery claim. Much work remains in understanding the exact size of standard model predictions, accounting for all sources of uncertainty, and investigating what patterns of deviations might be expected if various theoretical extensions are correct. As theoretical understanding improves, it may become clear that some anomalies are actually in better agreement with the standard model than initially thought, while others represent more significant deviations requiring new physics. Third, other experiments and observatories will provide complementary evidence. Precision measurements made by atomic and nuclear physics experiments probe the structure of fundamental interactions at scales different from those at CERN. Cosmological observations, measurements of the cosmic microwave background radiation, observations of distant supernovae, detections of gravitational waves, all provide windows into the properties of fundamental particles and forces. A genuine breakdown of the standard model should reveal itself across multiple independent experimental programs, not only at CERN. The convergence of evidence from diverse sources would be far more compelling than anomalies from a single experiment. And finally, there is the possibility that new facilities will be constructed to probe energies beyond those accessible at the Large Hadron Collider. Proposals have been advanced for electron-positron colliders, for muon colliders, for larger proton colliders. Such facilities would provide new opportunities to discover or constrain new particles and interactions. The question of whether such a facility will be built, where it will be built, and when it will come online remains open. But the scientific case for such a facility is clear. If the anomalies CERN has detected represent genuine new physics, a more powerful accelerator might reveal the new particles or forces responsible more directly than the subtle deviations observed so far. Part 12. How we know what we know. The discoveries emerging from CERN raise profound questions, not only about the nature of physical reality, but also about the nature of scientific knowledge itself. How do we know what we know? What constitutes evidence for a discovery? When can we claim to have found genuine new physics rather than merely statistical fluctuations? These are questions at the intersection of physics and philosophy, questions that have occupied the minds of physicists and philosophers of science throughout the modern scientific era. The scientific method, in its classical formulation, involves the formation of hypotheses, the design of experiments to test those hypotheses, the collection of data, and the interpretation of that data in light of the original hypotheses and competing alternatives. But the practice of science, particularly in particle physics, often proceeds in more subtle ways. Experiments typically do not directly test a single hypothesis, but rather constrain a space of possibilities. Measurements do not yield definitive yes or no answers, but rather probability distributions representing the likelihood of various outcomes given the data. The concept of statistical significance is particularly important here. Physicists have adopted a convention that a signal is considered evidence if the probability of observing the signal purely by chance, given the standard model's predictions, is less than 1 in 3,500, 3 standard deviations. A signal achieves the status of discovery only if the probability of it occurring by chance is less than 1 in 3.5 million, 5 standard deviations. These high thresholds reflect the recognition that even unlikely events occasionally occur by pure chance, especially when searching through large datasets looking for anomalies. The possibility of having found a statistical fluctuation rather than genuine new physics must be carefully guarded against. By these conventional standards, CERN's anomalies remain in the interesting category, suggesting new physics might be present but not yet achieving the statistical threshold required for a definitive discovery claim. This situation is actually quite common in science. Many important discoveries began as tantalizing hints that gradually accumulated evidence over years or decades. The discovery of the Higgs boson, for example, involved the gradual accumulation of evidence from multiple experiments until the signal became undeniable. The anomalies CERN is detecting may follow a similar path. But there is another philosophical dimension to CERN's discovery that is equally important: the question of how theories are chosen and evaluated. Physics seeks not merely to describe phenomena, but to explain them through underlying principles. The Standard Model is not simply a convenient formula for making predictions. It embodies certain theoretical values: simplicity, elegance, unification. A successful theory should be able to explain why nature is structured as it is, not merely describe how nature behaves. If the anomalies detected at CERN can be explained by extending the Standard Model in ways that preserve or enhance these theoretical values, then CERN may be pointing us toward a deeper and more elegant understanding of reality. The crack in the edifice might be the beginning of the construction of an even more beautiful cathedral. Part 13. Matter in the Cosmic Context. While CERN focuses on the realm of the infinitesimally small, probing the properties of particles and forces at the highest energies, it is important to remember that this investigation is ultimately in service of understanding the cosmos as a whole, from the first fraction of a second after the Big Bang to the present day, 13.8 billion years later, and onward into the far future. The early universe, in the moments immediately after the Big Bang, would have been inconceivably hot. So hot that all particles would have possessed enormous energies comparable to those produced in CERN's collisions. As the universe expanded and cooled, these high-energy states would have given way to the particles and forces we observe today. But the physics of that early era left imprints on the universe, subtle signatures that we can still detect billions of years later. Understanding these signatures requires understanding the fundamental particles and forces, which is precisely what CERN investigates. One such signature is the slight excess of matter over antimatter that allows the universe to contain anything at all. Another is the nature of the dark matter that comprises most of the universe's mass. A third is the spectrum of temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. These observations from cosmology provide powerful constraints on theories of fundamental physics. Conversely, theories developed through particle physics experiments can make predictions about what we should observe in the cosmos. The dialogue between particle physics and cosmology has become increasingly important in modern physics, with each field providing insights that guide the other. In this broader context, CERN's anomalies take on additional significance. If the deviations from the Standard Model are genuine, and if they arise from new particles or forces, these new physics might have been crucial in determining the properties of the early universe. They might explain why matter prevails over antimatter, why the universe possesses the dark matter it does, why the large-scale structure of the cosmos has the particular features it exhibits. Understanding fundamental particle physics is not merely an abstract intellectual exercise. It is intimately connected to understanding our own existence, our origins, and the nature of the universe that gave birth to us. Part 14. The Nature of Reality Reconsidered. In contemplating CERN's discoveries, one is inevitably drawn to meditate on the very nature of reality itself. What is the universe made of, ultimately? What are the fundamental constituents from which all existence is constructed? These questions have occupied philosophers and mystics for millennia, yet it is only in the modern scientific era that we have developed tools sufficiently powerful to investigate them in quantitative, testable ways. The quantum mechanical view of reality that has emerged from a century of physics is profoundly counterintuitive. Particles do not possess definite properties until they are measured. They exist in superpositions of multiple states simultaneously, resolving into definite states only when observed. They can be in two places at once. They can tunnel through barriers. They can become entangled with one another such that knowing the state of one instantly determines the state of another regardless of distance. This quantum reality is so strange that it has generated numerous philosophical interpretations. The Copenhagen interpretation, the many worlds interpretation, pilot wave theory, each attempting to make sense of what quantum mechanics tells us about the nature of existence. Added to this quantum strangeness is the relativistic perspective, inherited from Einstein's theories. Space and time are not fixed, absolute backgrounds against which physics unfolds. Rather, space and time are dynamical, shaped by the mass and energy they contain. They can be curved, warped, stretched, and compressed. Events that are simultaneous in one reference frame may occur in a different order in another reference frame. The universe's geometry is determined by its content. Reality, at both the quantum and relativistic scales, is far stranger and more wonderful than our everyday intuitions would suggest. The Standard Model, for all its successes, is built upon these strange foundations. It is a quantum field theory, describing reality not as a collection of definite particles, but as a collection of fields, quantum entities that permeate all of space and can fluctuate, producing particles that represent excitations of those fields. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. Quarks are ripples in the quark fields. The forces between these particles arise from the exchange of other particles, themselves excitations of different fields. This picture is extraordinarily abstract, far removed from our everyday experience of discrete, localized objects. And yet, this abstract mathematical framework makes predictions that agree with experiment to astonishing precision. The magnetic moment of the electron, predicted by the marriage of quantum mechanics and special relativity, is accurate to more than 10 decimal places. The properties of the Higgs boson, predicted by the Standard Model, align with observations to remarkable accuracy. How is it possible that mathematics, a creation of human minds, can describe reality with such fidelity? This is the profound mystery that contemplating CERN's work should inspire in us. We are creatures of the cosmos, made of the same atoms, and governed by the same fundamental laws as everything else. And within our consciousness lies the capacity to apprehend these laws, to express them in mathematical language, to use that language to make predictions about phenomena we have never observed. This mysterious conjunction of consciousness and cosmos, of thought and reality, remains ultimately inexplicable. Part 15. Pathways Forward. If CERN's anomalies do indeed point toward physics beyond the Standard Model, the implications for future research directions are profound. New experimental techniques would need to be developed to directly detect or constrain the new particles or forces responsible. Theoretical frameworks would need to be extended and refined to incorporate these new elements while maintaining consistency with all existing observations. The field of particle physics would enter a new era of discovery and investigation. But the significance extends beyond the technical domain of physics. Throughout human history, major revisions in scientific understanding have had profound cultural impacts. The Copernican revolution, which placed the Sun rather than the Earth at the center of the solar system, required centuries to become accepted but ultimately transformed how humans understood their place in the cosmos. The Darwinian revolution, which showed that all living things are related through common descent and natural selection, sparked philosophical and theological upheaval that continues to this day. Einstein's revolutions in understanding space, time, and gravity transformed our most basic conceptions of reality. A genuine discovery of new fundamental physics would represent another such transformation. It would demonstrate that our understanding of reality, while impressive, remains incomplete. It would show that there are still deep questions to answer, mysteries to explore, new lands to discover. In an age sometimes characterized by a sense that all the fundamental questions have been asked and most have been answered, such a discovery would reaffirm the enduring nature of the quest for understanding. It would inspire new generations of scientists to pursue careers in physics, attracted by the challenge of investigating genuinely new phenomena. Moreover, the methodologies developed at CERN have applications far beyond fundamental physics. The data analysis techniques developed to extract signals from noise, the machine learning algorithms trained on massive datasets, the precision measurement techniques, all have found applications in medicine, engineering, environmental science, and numerous other fields. The spin-offs from CERN's work have contributed to technologies that benefit society, from positron emission tomography scanners used in medical imaging to the World Wide Web itself, developed at CERN to meet the laboratory's data-sharing needs. Further discoveries at CERN might lead to additional practical applications we cannot yet foresee. Part 16. The Community of Inquiry. One cannot fully understand the significance of CERN's work without appreciating the human community that makes it possible. Physics is often presented as a body of abstract knowledge, timeless truths about the nature of reality. Yet physics is made by humans, and the pursuit of knowledge at CERN is fundamentally a human endeavor, shaped by the ambitions, curiosities, frustrations, and triumphs of the thousands of individuals who work there. The experimental physicists working at CERN spend years designing and building detector systems of staggering complexity, systems capable of detecting the traces of particles created in the collision and reconstructing their properties from these traces. These are not solitary endeavors. They involve engineers, computer scientists, technicians, and physicists working in coordination to solve problems and implement solutions. The theoretical physicists working on the interpretation of CERN's data are engaged in a global conversation, comparing their understanding, debating interpretations, proposing new models. Postdoctoral researchers and graduate students, the next generation of scientists, are trained in this environment, learning not only the technical details of physics, but also the cultural values of the scientific community: openness, rigor, the willingness to be proven wrong. The social dynamics of this community are important to understanding how scientific progress occurs. Individual researchers become invested in particular interpretations or theories, sometimes to the point of bias. Yet the peer review process, the requirement to present results at conferences and in journals, the critical scrutiny of colleagues, these mechanisms help to overcome individual biases and move the field toward truth. Science progresses not because individual scientists are perfectly objective, but because the scientific community collectively has developed institutions and practices designed to minimize the impact of individual subjectivity. Moreover, the international nature of CERN's collaboration demonstrates that the pursuit of fundamental knowledge can transcend political and national boundaries. Physicists from nations that have been in conflict, that currently maintain tense relations, work side by side at CERN. They share data, collaborate on analyses, publish joint papers. In an increasingly fragmented world, CERN stands as an example of what humanity can achieve when we put aside narrow national interests in service of a larger goal, understanding the universe. This alone, independent of any scientific discoveries, makes CERN an institution of profound significance. Part 17. Meditations at the Edge of Knowledge. As we contemplate the findings emerging from CERN, and as we consider what they might mean for our understanding of the universe, we find ourselves in a peculiar position. We have built an extraordinary apparatus for investigating nature's deepest secrets. We have developed sophisticated theoretical frameworks that predict the properties of fundamental particles with stunning accuracy. Yet we have also discovered that this framework, for all its power, appears to be incomplete. There are cracks in the edifice, anomalies that suggest something has been left out of our understanding. This situation, standing at the frontier of knowledge, with hints of something beyond but not yet clear what, is oddly reminiscent of standing on a beach at dusk. The sun is setting, the light is fading, and beyond the familiar shore lies the dark ocean. We can see its surface, can understand something of its properties, but its depths remain unexplored. The foam of the waves at the edge carries tantalizing signs of what lies further out. The slightly greater intensity of the waves, the subtle changes in the water's composition, the occasional glint of something moving in the deeper water. These signs suggest that there is more to discover, more to understand, more to explore. The uncertainty that characterizes the current moment in particle physics, where discoveries are suggested but not yet confirmed, where new physics seems to lurk just beyond the reach of current experiments, may itself be valuable. Uncertainty drives inquiry. Certainty, if it could be achieved, would allow science to rest. But the universe, fortunately or unfortunately, does not seem inclined to grant us the comfort of complete certainty. Instead, it parcels out knowledge gradually, revealing just enough to entice further investigation, and in each revelation placing us face to face with new mysteries. To be a physicist, or simply to take seriously the pursuit of understanding how the universe works, is to have made a commitment to following the evidence wherever it leads, to remaining open to being surprised, to accepting that fundamental principles of reality may be quite different from what we assume. It is a posture of humility before nature, combined with confidence in the human ability to understand. It is a recognition that the universe is genuinely interesting, that it holds surprises, secrets, depths we have not yet fathomed. And it is an affirmation that the effort to fathom these depths is intrinsically valuable, worthy of dedication and resources, part of what makes us human. Part 18. The Unfinished Symphony. In the coming years and decades, the investigation into CERN's anomalies will continue. More data will be accumulated, more precise measurements will be made, more theoretical work will clarify the implications of the observations. It is impossible to predict with certainty what will be discovered. Will the anomalies strengthen, becoming increasingly incompatible with the standard model and pointing towards specific new physics? Will new particles be discovered directly, their properties making clear the nature of the physics beyond the standard model? Or will the anomalies gradually diminish as measurement techniques improve and theoretical understanding deepens, revealing them to be nothing more than statistical fluctuations? Any of these outcomes is scientifically significant. If the anomalies grow stronger and clear new physics emerges, humanity will have made a genuine leap in understanding the fundamental nature of reality. If they fade away, the field will have learned that the standard model's domain of validity extends even further than previously believed, and the search for new physics will redirect itself toward other signals or phenomena. If they resolve into deeper understanding without invoking new particles, we will have gained insight into the subtle structure of quantum field theory itself. But whatever the specific outcome, the larger enterprise continues. Physicists will continue building more sensitive experiments, developing more powerful theories, training the next generation of scientists to carry forward the quest. CERN will continue operating and eventually be joined or replaced by ever more powerful machines. The community that gathers around these questions will persist, driven by the fundamental human urge to understand. This is how science advances, not through occasional flashes of brilliant insight, though those do occur, but through steady, persistent effort applied across decades and generations. Individual discoveries lead to new questions, which drive the search for new discoveries. The accumulated knowledge of centuries provides the foundation upon which each new generation builds. The crack that CERN has discovered in the Standard Model may be the first opening through which we catch a glimpse of deeper physics, or it may prove to be nothing more than a hairline fracture without deeper significance. But the very act of searching, of investigating, of remaining open to what nature has to teach us, is itself profoundly meaningful. Part 19. What binds the universe together? At the deepest level, the investigation at CERN is an investigation into what binds the universe together, the fundamental forces and principles that give it unity rather than allowing it to dissolve into disconnected chaos. We have learned that the forces we observe are unified in particular ways. Electromagnetism is a unified description of electricity and magnetism. The electroweak force unifies electromagnetism with a weak nuclear force. These unifications revealed that what appeared to be distinct phenomena were actually different manifestations of a single underlying principle. The anomalies CERN has discovered may represent the first hints of yet deeper unification, a principle of unity that encompasses even more of the universe's diversity of forces. Or they may suggest that the universe's structure is more complex than a simple hierarchy of unifications, that perhaps there are multiple ways that different aspects of nature can be understood, each valid within its domain, but each potentially incomplete outside that domain. The question of unity in physics is not merely technical. It embodies a profound philosophical commitment, a belief that the universe is not arbitrary, not a collection of disconnected domains with independent rules, but rather a coherent whole governed by discoverable principles. This belief, which has motivated physics since Newton, has proven justified again and again. Yet it also remains an article of faith, in the sense that there is no prior reason to suppose the universe must be unified. It could have been that every phenomenon required its own explanation, its own principles. The fact that it is not, that great diversity flows from simple underlying principles, remains one of the deepest wonders of existence. And as we investigate these binding principles, we also investigate the origins of meaning itself. Why is there something rather than nothing? Why does the universe follow mathematical laws? Why can consciousness understand these laws? These questions transcend physics in the narrow sense, reaching toward philosophy, theology, and the deepest concerns of the human spirit. Yet they are questions that physics, by investigating the fundamental nature of reality, touches upon. In seeking to understand the universe's binding principles, we are also seeking to understand ourselves, what we are made of, how we came to exist, what our place is in the vast cosmos. Part 20. In the Stillness Before Sleep. As we conclude this meditation on CERN's discoveries, we return to the beginning, to the contemplative stillness of the night, when the world is quiet and the mind turns inward, reflecting on the mysteries that surround us. Somewhere beneath the Swiss-French border, the Large Hadron Collider continues its work, night and day, year after year, crashing particles together in pursuit of understanding. Above, in the night sky, the same stars that have guided human inquiry since time immemorial continue their eternal dance, offering their light to anyone who takes the time to look upward and wonder. The anomalies CERN has discovered, these subtle deviations from the predictions of the Standard Model, represent something profound about the human condition and our relationship with the cosmos. They represent our capacity to ask questions about the fundamental nature of reality. They represent our willingness to build great machines and marshal vast resources in service of understanding. They represent the cumulative achievement of human genius, stretched across centuries and applied through the combined efforts of thousands of dedicated researchers. And they represent the humbling recognition that despite all we have learned, there remains far more that we do not know. In the face of such mystery, we might feel a sense of helplessness or despair. The universe is vast beyond comprehension, and our knowledge of it is vanishingly small by comparison. Yet this realization need not lead to despair. Rather, it can inspire awe, a sense of wonder at the beauty and strangeness of existence. It can inspire humility, a recognition that we are small, but also that we are part of something grand. And it can inspire determination, the resolve to continue investigating, to push further into the unknown, to seek to understand. The crack that CERN has found in the edifice of the Standard Model is not a sign of failure or incompleteness in human understanding, though it does reveal incompleteness. Rather, it is a sign that the universe still has secrets to reveal, that the pursuit of knowledge remains alive and vital, that there are genuine mysteries remaining to be solved. And in an age when much seems decided, when conventional wisdom often seems unquestionable, this openness to new discovery, this willingness to have our understanding overturned, is precious. It reminds us that the search for truth is more important than adherence to past certainties. Carl Sagan, whose poetic vision has guided much of this meditation, once wrote that science is a method for testing knowledge against the universe, for separating what we wish to be true from what actually is true. CERN, through its precise experiments and careful measurements, is engaged in exactly this process. It is testing our knowledge of fundamental physics against the universe itself. And the universe, through the anomalies that CERN has detected, is beginning to whisper that our knowledge, while impressive, remains incomplete. As we contemplate these mysteries before sleep comes, we can take comfort in knowing that this process will continue, that future generations of scientists will build upon the work of their predecessors, using ever more powerful tools and deeper insights to probe the mysteries of nature, that the conversation between human consciousness and cosmic reality, conducted through the language of mathematics and experimental verification, will deepen and evolve, that the universe, inexhaustibly strange and wonderful, will continue to reveal its secrets to those patient and dedicated enough to seek them, and that in this seeking, in this sustained effort to understand the fundamental nature of reality, we fulfill something essential in our nature as the universe becomes conscious of itself. Epilogue: The legacy of questions. The discoveries at CERN are not endpoints, but waypoints in humanity's long journey toward understanding. The crack that has been found in the Standard Model is not a tragedy but an invitation to probe deeper, to ask harder questions, to push further into the territory that remains unexplored. The physics of the future will stand upon the foundation that today's physicists have built, and future generations will likely look back upon our current understanding as primitive and incomplete, just as we view the physics of a century ago. This is not discouraging, it is exhilarating. It means that the quest will continue, that there will always be new mysteries to investigate, that human inquiry into the fundamental nature of reality will not soon reach an endpoint. It means that young people today, looking at the anomalies CERN has discovered, can see in them the seeds of future discoveries that they might help to cultivate. It means that the enterprise of physics, and more broadly the enterprise of science, remains vital and alive, capable of generating genuine novelty and surprising us with unexpected insights into the structure of the universe. And so we end where we began, in contemplative stillness, recognizing that we stand at a threshold between the known and the unknown. Behind us lies the accumulated understanding of centuries of scientific inquiry. Ahead of us lies territory unmapped and questions unanswered. The anomalies that CERN has discovered are lights pointing into that territory, suggesting paths for future exploration. Whether they lead to revolutionary discoveries or to refined understanding of phenomena already known, they beckon us forward, reminding us that the universe remains ultimately mysterious, that wonder and awe are appropriate responses to the fundamental nature of existence. In the silence and darkness of the night, as the Large Hadron Collider continues its patient work far beneath our feet, and as physicists across the globe continue analyzing data and developing theories, we can rest assured that the human quest to understand the cosmos continues unabated. The crack in the edifice may be the beginning of something magnificent, a deeper theory, a more complete understanding, a revolution in our conception of fundamental reality. Or it may be something more subtle, a refinement and extension of existing frameworks. But either way, it represents the unfolding of the human spirit's greatest adventure, the attempt to understand the universe that birthed us. And in that attempt lies the best of what humanity has to offer.